Hello, everyone. Today, in this session, we're going to have the fifth speech in our third algebra workshop in 5 November. And in this session, we're going to have Oussama Amir as our next speaker. And now, before starting, we want to learn more about Oussama Amir's Oussama Amir. Okay, Oussama, who are you and what are you doing? What are you working for? Can you tell us more about yourself, and then we can start your speech?
Okay. Hello, everyone. So my name is Oussama Amir. I am from Morocco, from Casablanca specifically. I am doing my master's in Sabancı University, studying mathematics. I also did my bachelor in Bilkent University. Currently, I am working with Professor Michel Lavrov. My main subject, let's say, is quantum coding theory and its relation with projective geometry and finite projective geometry. That's about it.
That's great, and I think it was enough to know you. And then we can start your speech, your presentation now. And before starting, could you please give us a short brief about your presentation? What it is about? A brief introduction, I mean.
Brief introduction. So there are these instruments or these operators known in physics mostly and in quantum computation and stuff like that. And these tools are measurements, and these, you can think about them as matrices, D by D matrices, a set of matrices. And they're very useful in a lot of, let's say, fields like quantum computation, quantum tomography, and stuff like that. And basically, there is a conjecture about these sets of operators called SIC-POVMs. The conjecture says that they exist in every dimension. We still don't know whether they exist or not. It's still an open problem. And today's presentation is going to be basically some introduction to the field, plus some algebraic properties we're going to talk about, and we're going to prove some theorems about these instruments as well.
Yeah, that sounds complicated, but also exciting.
Thank you.
So I think to understand that, we can start your presentation. Yeah, you can share your screen.
All right, let's go for it. Okay, can everyone see my screen?
Yes, we can.
All right, so today's presentation is going to be about algebraic properties of symmetric, informationally complete, positive operator valued measurements. It's a long name, I know, but somehow I know some people thought it was necessary to make it this long. Mostly we know this by its short form, so SIC-POVMs, and it's just the first letter in every word. Okay, as I said, symmetric, informationally complete, positive operator valued measurements are basically sets of positive semi-definite operators, or you can call them matrices, that were proved to be useful tools in many areas. And here we're talking about quantum tomography, quantum computing, and many others. The interest in SIC-POVMs is spanned by many important mathematical subjects. And here we talk about Hilbert 12th problem, the existence of Equiangular complex vector problem, and many other problems. And in this presentation, we're going to discuss a little bit of some algebraic properties of this SIC-POVM. So first thing we should know is that although these instruments or these operators are very useful, it is very hard to compute them. And usually the calculation of these operators tend to rely on some certain symmetries and algebraic properties that we're probably going to talk about some of them. And as you can see here, even in dimensions that are pretty small, let's say in a high scale, we're talking about dimensions between 122 and 151, we can see that the computational hour required to calculate these operators and to find just one set of them is very high. So up to now, the computational method has been useful, but in the same time, not very, let's say, not the best approach. Okay, first of all, let's start with the definition. So in terms of definition, I'm going to give two main definitions. So one of them is by Appleby in his paper in 2005. And he defined these SIC-POVMs as a set of operators, EM, exactly D squared operators, such that they satisfy these certain properties. The first one is that lambda times each one of these operators is a one-dimensional projector. When we say one-dimensional projector, that just means an operator that has an image that has one dimension. Okay, so a line, basically. You can think about it as a line. And the overlap, or when we say overlap, it just means the trace of EM times EN for M different from N has to be constant. Constant for all M and N. And here, the lambda that we talked about is fixed for all M. So it doesn't depend on M. And once we have these satisfied conditions, we say that this set of EMs is a SIC-POVM. The second definition is we call these operators a SIC-POVM if we have certain vectors in our Hilbert space of dimension D, such that we're going to get every one of the operators in terms of our vectors. So we're going to write it as a tensor product of these vectors, and we're going to divide by this number 1 over D. Also, these vectors have to satisfy this. So the inner product, or the absolute value of the inner product of different vectors squared, is equal to 1 plus D lambda mn over 1 plus D. Lambda mn is basically equal to 1 when m is equal to n is equal to 0 when m is different from n. Then if these are satisfied, we call this set of vectors SIC-POVM. Okay. As I said earlier, it was conjectured by Zauner that SIC-POVMs exist in every finite dimension, which is still not proven up to the time of this presentation. And this, of course, was conjectured in 1999 in his dissertation. Now we define covariance. So this is an algebraic property of SIC-POVMs, and it's basically just a group action. So we say that a group G acts transitively on a SIC-POVM if there exists a J from 1 to D squared, so one of these operators, such that the action of G on this operator gives you the whole set of the SIC-POVM. Okay? And when this action is happening and it's transitive, we say that SIC-POVM is covariant with respect to the group G. So this covariant word, it just means transitive action. Also, if we have EJ is equal to 1 over D tensor of psi J with psi J conjugate, then we say, or we call psi J a fiducial vector. And this is a naming that is used often in the literature, especially in the computational field of these SIC-POVMs. We now define the symmetry group of a SIC-POVM, since this property turns out to be very crucial in determining groups that act transitively on SIC-POVMs. So as we're going to see, like a group that acts transitively on a SIC-POVM is actually a subgroup of this symmetry group of the SIC-POVM. So we define it as follows. So basically, the symmetry group G is all the unitary operators from the special linear group of order D, such that their action on EJ gives you an element of the SIC-POVM. It gives you one element. We don't require some further, let's say, restrictions. Okay. So up to this day, all computed SIC-POVMs had a certain symmetry properties. And actually, more interestingly, almost all the computed SIC-POVMs were covariant with respect to a subgroup of the generalized Pauli group. And we're going to introduce the generalized Pauli group as follows. So basically define a canonical basis on the D-dimensional Hilbert space. And then we're going to define the two operators Z and X Z basically gives you a phase that depends on the numbering of the basis element. So Z of ER is basically going to be omega to the power of R times ER. And then X of ER just basically shifts you to the next basis element. So X ER goes to ER plus 1. Okay. Here, R is an element of ZD, finite group of dimension D, or order D. And omega here is just the phase exponential 2 to the power of I over D. Okay, it's a dp of unity. Okay, then we define these operators dp's, which is a combination, basically a rough combination between x and z. Here we define p as a tuple p1, p2, both elements of zd. And we're going to have dp as elements tau to the power of p1, p2 times xp1, xp2. Here tau is minus exponential of ipd over d. Okay, once we define these operators, now we can define the generalized Pauli group, or known also as the Weil-Heisenberg group. Depends on which literature you're reading. These two names are used interchangeably. So this generalized Pauli group is just going to be random, or not random, but phases of order 1. So these basically have absolute value 1 or order 1 times the operators dp's that we calculated. And these phases are what we use to allow us to get a group. So without these phases, you don't get exactly. That's why we have to add them. All right. Now we give a small example just to make sure everyone is on the same page. So if you take an easy dimension, so dimension 2, so X is going to be this matrix, and Z is going to be this matrix. As you can see, you have here X changes you to the next basis element, and Z added the phase adds a phase, so it's either +1 or -1. And the generalized Pauli group is basically going to be EIX zeta X to the power of A, Z to the power of B. Okay, here we have A and B are in Z2, not ZD. This is a mistake. So it should be Z2. And here you can see that we don't have tau. So if you remember, in the dp's in here, we had a tau, and we said that we're going to multiply E to the power of I zeta times dp. But in here, we don't have it because we can actually include it. That tau can be included in this random phase that we took. So just to simplify kind of the notation. Okay, now we talk a little bit about the Clifford group. So the Clifford group of dimension D is the normalizer of the generalized Pauli group in the unitary group. Okay, so the Clifford group obviously is a subgroup of the unitary group. And also, it is the main object of Appleby's theorem that we state here. And this theorem is very useful in terms of calculations as well, like especially in terms of the construction that was in the proof of the theorem that we're not going to present because it's too long. So this construction is useful usually in the calculation. So Appleby states in his paper in 2005, there exists a surjection from the special linear group to ZD bar. So D bar here is 2D if D is even, and it's equal to D if D is odd. So it depends on the oddness of D. And this is a semi-direct product with ZD squared. Go into the Clifford group quotient, the group ID. And the group ID is basically just omega i's for all I multiplied by the identity matrix or identity operator. Okay, here we remind you, so omega is basically exponential of 2 pi I over D. All right. So again, we go back to the conjecture. So now I want to be a little bit more precise. So as I said, Zauner conjectured in 1999 in his dissertation the existence of SIC-POVMs in arbitrary dimensions, but exactly what he conjectured, or his exact conjecture, is as follows. So for every dimension larger than 2, there exists a SIC-POVM whose elements are the orbit of a positive rank 1 operator. And this is If you remember, this comes from the fiducial vector, and this is the element that when you act on with the group, it gives you all the elements of the SIC-POVM. And also he says that the group that is acting on E0 is the Pauli group, or the generalized Pauli group. Also, he gives more information, which is very useful in computation nowadays, is that E0 commutes with an element T of the Jacobi group, which is defined as follows. So is the generalized Pauli group, semi-direct special linear group 2ZD. And the action of T on the generalized Pauli group, modulo the center has order 3. Okay, this is the general conjecture. So Appleby's theorem is the main tool to study the orbits of SIC-POVMs, because we know that the Clifford group is the normalizer of these groups. So also it's very useful to prove the second part of Zhu's theorem, which we won't be talking about right now. But we're going to talk about the main theorem of Zhu in one of his papers about SIC-POVMs, which is as follows. Of course, this was published in 2010. Probably not many or none is familiar with this theorem, but it's somehow very important in the literature for SIC-POVMs. So it states that in any prime dimension not equal to 3, each SIC-POVM acted on transitively by a group is acted on transitively by the generalized Pauli group. So what does that mean? It means that when you have a prime dimension, if you take a SIC-POVM, we don't know if it exists or not, but if it existed and it's acted on transitively by a random group, then it's also acted on transitively by the generalized Pauli. And he also adds that the symmetry group is a subgroup of the Clifford. Okay. Good. Now we introduce some lemmas and propositions that will facilitate, let's say, proving the main theorem. Okay. So we start by a lemma by Zhu as well. So in any finite dimension, if a SIC-POVM is a group covariant with respect to a special unitary group, then G is necessarily non-abelian. Okay. In particular, the symmetry group of such SIC-POVM is non-abelian. Okay. Again, this is clear. So if you have a finite dimension and your SIC-POVM is group covariant, or there is a group that acts on the SIC-POVM transitively, then this group has to be non-abelian. And sorry, all right. So in the proof, it goes as follows. So since these elements or this group has elements which are unitary, then they can be simultaneously diagonalized. So we take them in diagonal form. Let's say we have an A in G. G is our group, and it's going to be of the form B1 going to BD. And then we take E1 to be our fiducial, or we take E1 to be the operator that will span all the other operators by the group action. And psi1 is going to be the fiducial vector as we defined earlier. So here we have, by the fact that psi1 is a fiducial vector, we have that for every j, there exists an A basically in G such that psi j is equal to A times psi1. So psi1 generates all the other psi j's using the group action of the group G. Okay, and this gives you in terms of components, if you want to write it in terms of components, is going to give you that AJK is equal to BK times A1K. And AJK is basically the kth component of psi j, and A1K is the kth component of psi1. All right. Now we move to absolute value, or the order, whatever you want to call it. So the absolute value of AJK is going to be equal to absolute value of BK times absolute value of A1K. And because BK has to be 1, AJK is going to be equal to A1. Now here we used another properties of SIC-POVMs is that when you add up all the operators, they give you the identity, and therefore you have this equation. And if we move to the kth component of this operator, it's going to give you this equation after absolute value. And therefore, we have that for every k and j, every k and j, we have a1k absolute value is equal to absolute value of ajk, which is equal to 1 over square root of b, coming from this equation. So without loss of generality, let's assume that A does not stabilize psi1. So again, if A doesn't stabilize, does stabilize psi1, we can take another element, but let's just stick with A. That gives you that d squared times the absolute value of psi1 u psi1, and this u should be A. Sorry for the mistake. So this u should be A. This is equal to sigma of bi squared, which is equal to d squared over d plus 1. So now we move to some words. So here we notice that bi's are algebraic integers, since they are d roots of the unity, as you can see here. So these sigma of bi's are an addition of d roots of unity, which are algebraic integers. And the expression in the middle of the equality is an algebraic integer, which is what we just said. But the fraction, at the end cannot be an algebraic integer. So this number, d squared over d plus 1, cannot be an algebraic integer. Why is this one? Because the GCD of d and d plus 1 is equal to 1, as most people can tell. So hence we have a contradiction. We have two, let's say, numbers that are equal, but they cannot be equal, because one of them is an algebraic integer and the other one is not. Therefore, we have proved the first part of the proposition. The second part is also trivial, since the SIC-POVM is acted on transitively by symmetrically. So we just proved that if a group acts transitively on a SIC-POVM, then this group cannot be abelian. And here we just we state that the symmetric group acts indeed transitively on a SIC-POVM, therefore it cannot be abelian. That's good. So now we move to the next lemma, where we don't have a lot of time left. So in a prime dimension P, if a SIC-POVM is covariant with respect to some group, then this SIC-POVM is covariant with respect to every silo P subgroup of G. And how do we prove that? So basically, we have, I can just show it in this graph like very quickly. So basically here we have the stabilizer of G of EI and G, and this has index P squared. Why? Because the orbit of EI in G is equal to P squared. So we have P squared elements, and this comes from, again, from algebra. And here we have the index of S over P prime, and P prime is the silo subgroup, silo P subgroup of S. And this has to have index N, and also P does not divide N. Why? Because P prime has the largest order of P. Okay, also here we have the P subgroup, P silo subgroup of G, P, which has index M over G. And also P does not divide M. Why? Because P has the largest power of P out of the order of G. And P prime is also a P group of G, which means it's a subgroup of the P silo subgroup of G. So by this identification, we can see that P squared times N is equal to M times X. N and M are not divisible by P. That means that X has to be P squared. Okay, and P it has to be equal to P squared. And note that what we have here, this P prime, is a subgroup of the stabilizer of EI in G, which means it is the stabilizer of EI in P. That means that P squared, which is X, is exactly the order of EI in P. And what does that mean? That means that EI, the order of, again, the orbit of EI has P squared elements, which means that acting on EI, you can get P squared elements, and the number of SIC-POVMs is exactly P squared. So that means that this P silo subgroup acts transitively on the SIC-POVM. Again, we have another lemma. This comes from a little bit of representation theory. So we have let P be a non-abelian P silo subgroup with order P to the power of K larger than P to the power of 3. then the following fateful representation is irreducible. And we do that by a way of contradiction. So let the representation of P be the vector space V. We know that the dimension of Rho is equal to P, and the order of P is equal to P to the power of K. So let Vi be irreducible, or I mean, Vi is irreducible means that Vi is equal to P to the power of J. Let the representation of P be the vector space V again. So assume that V is equal to some direct product of inner direct product of VIs, where VIs are irreducible. Then you have the order of Vi is equal to Di, which is equal to P to the power of J, and also the dimension of V is equal to B, so to P. So P is equal to basically the summation of Di's. All right. What does that mean? That means that these VIs have to be equal to 1, because they are dividing P, so they can be either P or 1. Since they cannot be P, we're assuming there is multiple spaces. That means that each one of them has to be 1, which implies that P is abelian, which is a contradiction because we're assuming it's not abelian. Hence, this representation has to be irreducible. Now, in the last theorem, so in any prime dimension, group covariant SIC-POVM is necessarily covariant under the action of the Pauli group. And we try to be a little bit faster, I guess, to respect our time. So, sorry. So, consider a SIC-POVM that is covariant with respect to group G. Okay. So, in a prime dimension P, of course, we're assuming the dimension is prime, and let P be a Sylow P subgroup of the symmetrical group of the SIC-POVM. Okay, so this SIC-POVM is covariant with respect to P, as we proved earlier. So if a group acts transitively on a SIC-POVM, then its pillow subgroup also acts transitively on the same SIC-POVM. So this is good, and hence P cannot be abelian, since we said if it acts transitively, it cannot be abelian, which implies that the order of P is greater or equal to P to the power of 3. And this is from algebra. Then P is an irreducible representation of itself. Since P is basically a set of unitary matrices, we can look at it as a representation of itself. So the order of the center of P is at least P. All right, since P is irreducible, that implies that every element of the center is of the form lambda I. Else, P would have a non-trivial subrepresentation, which contradicts the fact that we stated earlier. So each element of the center of P is an element of the special linear group of order P. And that means that the center is basically the elements A of P that are equal to lambda I, which is equal to the group omega I, where omega, this is omega, is a pth root of unity. So that means that omega to the power of P is equal to 1. All right, so we now we take the quotient group over omega I, and this is also a P group, since omega I has order P and P has order P to the power of K. So hence this group doesn't have a trivial center, which implies the existence of a non-trivial element x prime in P, such that x prime, so we're taking the coset x prime omega I, has to be in the center of P omega I. We can also pick another element z prime from P omega I, such that this element commutes with x, since they are both in the center. So here we have x prime z prime is equal to z prime x prime omega I, which means if you turn it into the set, so from the quotient group to the actual group, this gives you z prime x prime minus 1 x prime minus 1 is equal to omega to the power of Ki. Now take a power of z prime so that we can reduce this K to 1. We just want omega I. This is doable, and without loss of generality, we take z prime to have this property such that K is equal to 1. And now we can assume that P is a monomial form, because P is an irreducible representation. And the group of monomial P by P matrices can be expressed as dP sigma P, where dP is diagonal matrices and sigma P is basically permutation matrices. Take SP as a subgroup of sigma P. This is a group of order P generated by the permutation 1 to P. So 1 goes to 2, 2 goes to 3, 3 and so on and so forth. And AP is a diagonal group, diagonal subgroup of the diagonal group dP and P. So it's basically a subgroup of P and D and D. P contains a conjugate of SP because it is the smallest P subgroup or P group of the group of permutations, and P is not abelian. Hence, it's not diagonal. So P cannot be diagonal, so it includes a conjugate of SP, which is a subgroup of sigma P. Okay, I know this the stuff that I stated before is kind of confusing, so this graph might help you see the structure of these groups and where X is and where Z is. So X is going to be in SP, and Z is going to be in dP, and this is basically the structure that we have. All right, so we can assume that Z prime is in D, SP, D minus 1 for some certain D. Hence, by the unitary transformations we get, so X prime Z prime goes to X double prime X by some unitary transformation U1, and then X double prime X goes to X triple prime Z by some unitary transformation U2, and then lastly we go to XZ by unitary transformation U3. Therefore, we are identifying P with the Pauli group through a unitary transformation. Lastly, we proved the covariance of our SIC-POVM with respect to the Pauli group. So assume for a contradiction that the stabilizer of the SIC-POVM in the Pauli group is not trivial. This implies, without loss of generality, that Z, for instance, stabilizes the fiducial vector. So we're going to take just like a vector that is stabilized by Z, and Z being like, you know, without loss of generality, we take Z. We can take a combination of Z and X, but we just take X. We just take Z because, I mean, it's the easiest case to do it. So if psi is stabilized by Z, that means it's an eigenvector of eigenvalue 1 for Z, which means it's of the form this 1, 0 or A0, 0, 0. That means that psi and X psi are orthogonal, which is a contradiction for our SIC-POVM. Remember, X switches from one canonical basis to the next one. So if you take X psi, it's going to be 0A0, 0, 0, which is orthogonal with psi. But this is a contradiction because we know that our SIC-POVMs, the vectors that construct our SIC-POVMs cannot be orthogonal since they have well-defined inner products between them. Okay. So the stabilizer of the SIC-POVM is trivial, which means the SIC-POVM is covariant with respect to the Pauli. And this is about it for the presentation. These are some citations, and hopefully everyone is still awake. Yeah, thank you for listening. Can you hear me?
Yeah, we can hear you clearly. So would you want to add up something or anything? Because we do still have 8 minutes.
So it's left for questions. If anyone has a question, they can present. They can, I mean, we can talk about it.
Okay. And Zoom, is there anyone who has questions? And I'm looking to YouTube as well. And now I think I can switch to Turkish. Oussama, please pardon me.
No problem.
Arkadaşlar şu anda hala 8-7 dakikamız var ve Çalıştay'ın bu konuşmasında Oussama'nın konuşması bitmiş bulunmakta. Ama sorularınız açık hala. Sorusu olan varsa şu an mikrofonu açıp sorabilir. Ben çevirebilirim veya sohbete yazabilir. Bir sorusu olan var mı? YouTube'da herhangi bir sorusu olan var mı? Evet, YouTube'da da yok. Aybüke, bana bir yardımcı olur musun? Şu anda ne yapmamız gerekiyor? Oussama, we don't have any questions in Zoom or in YouTube. And now there's one thing left to do, and it is to take a photo of your speech. So, arkadaşlar, kameralarını açabilirse çok güzel olur. Hatıra fotoğrafı zamanı. Herkes kamerasını açabilirse çok güzel olur.
Sunumu kapatmasını ister misin?
Oussama, can you please? Okay, that's great. You close your presentation. Ulgar, I think we are ready to take photo.
Ben alıyorum.
Oussama, first of all, we want to thank you for your presentation. It was so great that it does help us to think outside the box.
Thank you.
Because as a high schooler, to be right, I didn't really understand what we are talking about. I couldn't understand the details of your speech, but it did help me to expand my horizon. And I think the ones in bachelor's or in their masters learned lots of things from your speech and from you, especially because I think it was very encouraging to speak here. So as TMK, Turkish Maths Club, we are very proud to have you and your speech today. Thank you.
Just if I can say one thing before, I mean, maybe most of the people that would be listening would be, let's say, in undergraduate. And I just want to say, like, often when we go to listen to some mathematical speeches or something like that, we find ourselves mesmerized and just not understanding what's going on. And it happens even in graduate level. Like, even professors have this problem. If they go to something that they're not an expert in, they just go there and they look at this mathematical stuff going on and they can't understand anything. And this is very normal. And what it shows you our ignorance. There is no person who knows everything. It's just you go somewhere and maybe I will go listen to a speech, even that is happening in today, for example, other people's speeches, and I won't understand most of it because, again, we're just ignorant beings. We know a little bit, and that's about it. We try to, learn more, and that's about it.
Yeah, that's right. But from what I learned today is that one day I want to be just like you. One day I will be not the listener or not will be the moderator that does not understand anything, but just hosting the speech. But I want to be the one that is speaking, that is sharing his information with the others. I just want to be like you.
That's great to hear. That's great.
You did expanded my horizons, and personally, I do thank you a lot. Thanks a lot. And
thank you.
As our club, it's an honor to have you here and your speech.
It's my pleasure. You. My pleasure. My pleasure.
I think we can close our session here. Is there anyone who wants to add something? I think no.
All right.
That's all for today.
It was a pleasure. Thank you so much.